So, welcome to the lecture series on mathematical methods and applications. So, now we will discuss Fourier half range series. We have already discussed in the last lecture how we can find out Fourier series expansion of even and odd functions, that we have already seen in the last lecture. Now, half range series, Fourier half range series, let us see. Half range series plays an important role in solving several engineering and physical applications, where it is required to get the Fourier series expansion of a function in an interval say 0 to L. So, it is a half range basically. In Fourier series, basically in the expansion of Fourier series we need interval minus L to L, okay, and function must be periodic. That is a condition for the Fourier series expansion of a function f(x). Now, here the Fourier series expansion of a function is in the interval 0 to L, where L is an half of the period. Okay. Now, how can we find out Fourier series expansion of such a function? And these problems are important in several engineering and physical applications. Okay. Now, it is possible to extend the function f(x) to the other half, that is minus L to 0 of minus L to plus L, so that f(x) is either an even or an odd function. Basically, what we do, we know the nature of the function from 0 to L, and that is given to us. Okay. And depending upon the basically nature of the function, we find out, we either extend the function considering function as an even function, or we either extend the function taking function as an odd function. Okay. Suppose function is given to you from 0 to L. Suppose this function is given to us from 0 to L. Okay. This function is given to you from 0 to L. It is a half period. Okay. Now, you can find out the even extension of this function. You can extend this function as an even function from minus L to plus L. Okay, and then find out the Fourier series expansion of this function. Okay. So, you can take this function as an even function, whatever function is given to you from 0 to L, you can find out the even extension of this function taking function as an even function. On the other way, you can also find suppose this is given to you from 0 to L, you can find an odd extension of the function. Okay. So, you can extend this function like this from 0 to minus L to plus L, and in the same way over here. Okay. In the same way over here. So, basically we need a Fourier series expansion of a function which is given in the half range from 0 to L. So, we can either, to find out the Fourier series expansion of such a function, we can either extend the function taking function as either as an odd function or taking function either as an even function. Okay. So, in the first case it is called as even periodic extension of f(x), while in the second case it is called an odd periodic extension of the function f(x). If we do an even periodic extension of f(x), which is the first one, which is the first case, it is the even extension of the function f(x), then f(x) is an even function in minus L to plus L, of course it is an even function. Then f(x) has Fourier cosine series, that we already know, that if function is an even function, okay, we extend the function as an even periodic function, then f(x) will be an even function, and in even function we only have a cosine series, cosine terms in the Fourier series expansion. Now, if we do an odd periodic extension of the f(x), then f(x) is an odd function in minus L to plus L, and therefore f(x) has Fourier sine series. Okay. Suppose we extend the function as an odd periodic function. So, this f(x) will be an odd function, and we know that if function is an odd function, then it contains only sine terms. The Fourier series expansion of that function will contain only sine terms. Okay. If a function is defined on a half interval from 0 to L, then we can obtain a Fourier cosine or Fourier sine series expansion by suitable periodic extensions depending on the problem. Okay. If we want a Fourier cosine series expansion, that means we take an even periodic function, or we take function as an even function, and if we want Fourier sine series, that means we will take as a odd extension, odd periodic extension of the function. Okay, that depends on the problem. So, suppose you want Fourier sine series. Okay, so we already know this result, that if we want Fourier sine series, now function is given in 0 to L. Okay, and you want an odd extension of the function. Odd extension means only sine terms. Okay, so what will be the Fourier series of that function? The Fourier series of that function will be nothing but it will be given by a summation n from 1 to infinity Bn sin n pi x by L, and where Bn is nothing but 2 upon L integral 0 to L fx sin n pi x by L into dx. Okay. So, this is an odd extension of the function. Okay. Now, if we want Fourier cosine series expansion of the function defined on a half range from 0 to L, so that will contain only cosine terms. So, that will be given by a naught by 2 plus summation a n cos n pi x by L, n varying from 1 to infinity, and here a naught will be nothing but 2 upon L integral 0 to L fx dx, and a n will be given by 2 upon L integral 0 to L fx cos n pi x by L into dx. So, this will be the even extension of the function. Function is given from 0 to L, and we defined an even extension of function as a cosine terms, in the form of cosine terms. Now, let us try to solve this problem. Obtain cosine and sine series for fx equal to x in the interval from 0 to pi, and hence show this result. Okay. So, first of all, function is given, function is x, fx equal to x, a very simple function fx equal to x, interval is 0 to pi. Now, suppose we want cosine series expansion of this function. Cosine series expansion means we want to extend this function as an even function. We want to extend this function as an even function. So, this function is like this, it is from 0 to pi it is x, okay, fx equal to x from 0 to pi, and we want to extend in the function as an even periodic function. So, from minus pi also, if it is an even function, it must be symmetrical about x axis. So, we will draw this function like this, we extend this function like this, and similarly here also like this, similarly here also like this, and similarly here also. This will be an even extension of this function, or now we can write this function in the cosine series form. How fx will be nothing but a naught by 2 plus summation a n cos n pi x by pi, okay, n varying from 1 to infinity. And what will be a naught now? It is 2 upon pi integral 0 to pi. So, here pi cancels out, 0 to pi fx dx. Fx is nothing but x dx. So, it is nothing but 2 upon pi, it is x square upon 2 from 0 to pi. So, it is nothing but 2 upon pi square by 2 minus 0. So, it is nothing but pi. So, a naught is nothing but pi, okay, and a n, what will be a n? A n will be nothing but 2 upon pi integral 0 to pi fx cos nx dx. So, it is equal to 2 upon pi integral 0 to pi. Now, what is fx? Fx is x. So, x cos nx dx. So, now we will apply integration by parts to simplify this expression. So, this will be nothing but 2 upon pi. So, first as it is integral of second sin nx upon n minus derivative of this and integration of this, so nothing but minus cos nx upon n square 0 to pi. Okay. So, that is further equal to 2 upon pi. Now, the first term is 0 when x is pi or x is 0. Okay. Now, second term is 1 upon n square times, when x is pi it is minus 1 ki power n, and when x is 0 it is 1. So, this will be this term. Okay. So, this a n is equal to, now when n is odd, so this is nothing but, when n is odd it is minus 1 minus 1 minus 2 minus 2 minus into 2 minus 4 upon pi into n square. So, this will be nothing but this term when n is odd, and when n is even it is nothing but 0, because minus 1 ki power even is 1, 1 minus 1 is 0. Okay. So, a n is defined like this. So, what will be the cosine series of this function f x? So, a naught is pi. Okay. A naught is pi. So, it will be nothing but pi by 2 plus summation n from 1 to infinity, it is 2 upon n square pi minus 1 ki power n minus 1 into cos nx, which is further equal to pi by 2 plus 2 upon pi can come out, and when n is odd it is minus 4 upon, it is I mean 2 will, minus 2 will come out. So, when n is odd it is minus 4 upon pi into 1 by n square, that is cos 1 upon 1 square plus cos 3x upon 3 square plus cos 5x into 5 upon 5 square and so on, and when n is even it is 0. Okay. So, this will be the expansion of x, f x is x. Okay. So, this is an even extension of the function x. So, x is defined in only 0 to pi. We extend this function, take assuming the function as an even function. Okay. And that will contain only cosine terms. These are the cosine series expansion of function f x equal to x. Now, to reduce this expression 1 square, 1 upon 1 square, 1 upon 3 square, 1 upon 5 square and so on with all plus signs. Okay. We can simply substitute x equal to 0. So, put x equal to 0 both sides. So, when you put x equal to 0 it is pi by 2 plus or minus 4 upon pi, it is 1 upon 1 square plus 1 upon 3 square plus 1 upon 5 square and so on. So, that implies 1 upon 1 square plus 1 upon 3 square plus 1 upon 5 square is simply equal to pi square by 8. Okay. So, that we have proved this result also. Now, to obtain Fourier sine series of this function f x equal to x. So, how we will obtain that? The first part is over of this problem. Now, we want to obtain Fourier sine series of this function. That means, we have to extend the function f x equal to x as an odd function. Okay. Then only we can obtain Fourier sine series, that is the series containing sine terms only. Okay. So, how can we do that? We have the function f x equal to x here. Okay. We have the function f x equal to x here, it is y equal to x. Okay. And we have to extend this function as an odd function to obtain the Fourier sine series of this function f x equal to x. So, it must be like this, and assuming function as periodic function, we can extend this function as an odd function. Okay. So, what will be the Fourier sine series of this function? It will be summation n from 1 to infinity bn sine nx, okay, where bn is nothing but 2 upon pi integral 0 to pi fx sine nx dx. Okay. So, this is nothing but is equal to 2 upon pi integral 0 to pi fx is x sine nx dx. So, this is nothing but 2 upon pi integral of this is x into minus cos nx upon n minus derivative of this and integration of this will be minus sine nx upon n square from 0 to pi. So, after integration by parts we obtain this thing. So, this is nothing but it is 2 upon pi, when you put x equal to pi here or 0 here, this term is 0, okay, and here when you put x equal to 0 to it is 0. So, only one term is left here, so negative will come here, so it is pi into minus 1 ki power n upon n. Okay. So, pi cancel out, so it is nothing but minus 1 ki power n plus 1 upon n. So, this will be 2 into, okay, 2 into minus 2 1 ki power n plus 1 upon n. So, this will be bn. So, what will be fx? Fx will be nothing but summation n from 1 to infinity bn is 2 into minus 1 ki power n plus 1 upon n into sine nx. Okay. So, this is nothing but 2, when n is 1 it is sine x upon 1 minus sine 2x upon 2 plus sine 3x upon 3 and so on, or fx is x. So, this will be the odd extension or the sine series expression of the function fx in terms of sines. So, this will be the final solution of this problem. Okay. So, now let us try to solve one more problem of this function, which is we find as an, this function is also given from 0 to 1, okay, and that is in half range, and we want function to expand as an Fourier sine series. That means we want an odd extension of this function. Okay. So, how we can expand this as an odd function? So, again for the odd extension, that is we want the Fourier sine series of this function. So, the fx will be given by this expression. So, what will be bn? Bn will be nothing but 2 upon L. Now, here L is 1, okay, in this problem L is 1, 0 to 1 fx, and here also it is sine pi x upon 1 because L is 1, okay, fx sine n pi x upon 1 into dx. Now, we have to split the function from 0 to half, it is 1 by 4 minus x, from 0 to half, okay, from 0 to half, okay, sorry, 0 to half it is 1 by 4 minus x into sine n pi x dx plus half to 1, it is x minus 3 by 4 sine n pi x into dx and whole 2 times. Okay. So, we can simplify this to find out the sine series expansion of this function. Okay. So, how we can simplify? The simplification is simple, we have to apply by parts only. 2 times it is nothing but 1 by 4 minus x into minus of cos n pi x upon n pi, okay, and minus derivative of this, which is nothing but minus 1, and integration of this, which is nothing but minus sine n pi x upon n square pi square, okay, and that whole from 0 to 1 by 2. Okay. I simply apply integration by parts. Okay. First as it is, integration of second minus derivative of this and integration of this, which is nothing but this. Again for the second part, plus 2 times, again 2 is here. Okay. For the second part it is x minus 3 by 4, that you can easily solve by your own. You can easily apply integration by parts and simplify to find the Fourier series expansion of this function. Okay. So, it is nothing but minus cos n pi x upon n pi, and it is minus plus 1 into minus sine n pi x upon n square pi square, and it is varying from half to 1. So, so after simplification what we will get 2 times. Okay. So, when x is half, 1 by 4 minus half is minus 1 by 4, minus minus plus. So, it is 1 by 4 into cos n pi remains same into cos n pi by 2. Okay. When x is half here, it is nothing but minus of 1 upon n square pi square, and when n is half it is sine n pi by 2. Okay. When x is 0 it is 0, when x is 0 it is 1 upon 1 by 4, so that is minus minus plus 1 by 4 into n pi. Okay. Now for this term, okay, when x is 1 it is 1 minus 3 by 4, that is 1 by 4, okay, negative is here. So, minus 1 by 4 and pi into minus 1 ki power n, and when x is 1 here it is 0. Now, when x is half, it is half minus 3 by 4, half minus 3 by 4 is minus 1 by 4. Okay. So, it is minus 1 by 4 minus minus plus 1 by 4, okay, and minus is again here, so it is minus, and then it is cos n pi by 2 upon n pi, and when n is half here it is nothing but minus minus plus and minus again, so it is sine n pi by 2 upon n square pi square. So, you can simplify this entire expression, okay, to find out the value of Bn, okay, and that Bn you can substitute here to find out the Fourier series expansion of this function f(x). Okay. Now, in the same lines, we can also find out the Fourier series expansion of x sin x as a cosine series. Cosine series means we want an even extension of this function. So, that means for this function x sin x, you will simply find a naught and a n, and a naught will be given by so for this problem a naught will be given by 2 upon pi integral 0 to pi x sin x dx, and a n will be given by 2 upon pi integral 0 to pi, it will be x sin x into cos n x dx. Okay. So, this is how we can find out a naught and a n in this expression, and finally for some x we can also find out this series expansion of this function. Okay. So, thank you for this lecture. In the next lecture, we will study an identity and some problems based on that, and also complex form of Fourier expansion. So, thank you.